Hi, everyone. Thanks for joining. I'll be talking a little bit about our experience in computer vision. I would like to ask you, is there anyone here who is working on computer vision? Or we are all vector database persons? Yeah, so we have a few. So I hope it will be also interesting to people who are not fully active working on computer vision. So this is me, a little about my background. I did PhD at the Hebrew University, followed by a postdoc in Carnegie Mellon, followed by a startup I opened with my advisor, Professor Carlos Gestrin, who is now in Stanford. And we worked on an open source project called GraphLab, Graph Analytics. It will become clear why it's important. And I have here also my co-founder is also holding a PhD, Amir Alush from Bar-Ilan University, and a seasoned computer vision. So this is a joint work of the three of us. And after we had a startup, we started it in Seattle. We were acquired by Apple and joined Apple and did the infrastructure, deep learning infrastructure team of Apple, which is now 500 people in Seattle. And specifically, I was assigned with the task of working on computer vision for Apple factories. So I worked a lot on the watch and the iPhone. You can see here a metal enclosure of the watch as an illustration. But I had a couple of computer vision team, but the thing that was frustrating, we found out we're not dealing a lot with algorithms. We mainly did data preparation. This is because data from Chinese factories was very noisy. There were a lot of annotation mistakes. We had a few times we have to go to China, sit near the annotators, complain about annotation, throw the whole batch of information and start over again. So the model building was pretty slow and frustrating, and we had a lot of data issues. And I spent 5 years at Apple, and after quitting Apple a year and a half ago, I started thinking, what can we do to change this? And maybe this is just a problem which is evident only in Apple, in China, in factories. Maybe it's not a whole world problem. So I took a year off and started looking at some visual data set to understand what are the issues with their quality. So the first, we started to look on very famous computer vision data sets. So the computer vision guys in the audience may know it, ImageNet. It has 32,000 citations or more. And it was very, very carefully hand-curated and should have been very high quality. So we started with this data set because it contains 13 million images. It's a nice data set to play with. And what we found in this data set, there were tons of bad information, starting from broken images, things that were collected by mistake. There was no content on the image. So the title said the washing machine, and we had an image saying no image available. So that's completely unuseful for our model. We have tons of duplicates. This is a subset we used, which we found there are more than 10% duplicates, which are exact. And this is annoying from a few reasons. So it's not just blows up your storage, slows down your compute, but also may reduce the quality of your model. So this is a nice study recently published by a third party, by RoboFlow. It's a computer vision team, which infrastructure team, which shows they use our tooling to clean some of their data set, and there was significant reduction in cloud costs, but model quality was the same. And we are also aware of cases where you clean the data set, and suddenly also model quality goes up, even if you just remove duplicates. Another thing that we found, and it was a bit funny, Alibaba said, oh, ImageNet is very noisy data set, let's clean it. They had a clean version, and they released a train test split, but then we found out they had 100,000 images both in the train and test. So of course, that's a bad thing, because it confuses your metric, and you think your algorithm is good, where it's actually not that good. So that's a pity. In addition, there are a lot of funny issues in the data set. For example, here we illustrate wrong labels. So imagine a human annotator see this red wine and try to understand what's inside. So some of them may say This is red wine, Bordeaux, Beaujolais, Merlot, and so on. There is no consistency, and this image appears more and more times, and that simply doesn't make sense. You cannot train a model, and all the images are simply the same. Another interesting thing we found, there are images, for example, that are completely blank, white image, and they have this very weird title, captions, and you know I'm not a native English speaker, so I don't really know what's a windlass. And anyone knows what's a windlass?
Yeah, sailing.
Okay, so that's good to have someone native here. But this white image appears more and more times with different titles. That, again, completely confuses the model. There is no sense in it. Now, you may ask me, why are you talking about ImageNet? That's old-fashioned. We don't care. It was 12 years ago. Let's do generative AI. Everything is changed. Everything is much better. So I want to show you, you're probably wrong. So we have this generative, very cool model from Salesforce called Blip doing captioning. We took the same white image to the Blip model, and we got this title, "There is a man riding a surfboard on the beach." Now this is completely doesn't make sense. It's pretty funny, and it means the author of this captioning model didn't do the first order sanity checks on their data, and that will also happen in any generative algorithm. Now, this is a few more weird examples we found. So we have this very weird Chucky-like figure, and you can see you have the image ID. If you don't believe me, you can go check on ImageNet. Anyone can guess what was the label of this image? Yeah, no. So, not a man on surfing on the beach. The label was tire chain, and it's very weird because it's not the main topic of the image. There is some chain here, but imagine a generative model. You ask him, please generate a tire chain, and you get this frightening Chucky image. So that will be totally hilarious, and that will happen because those models are pretty stupid, I must tell you. Another funny example is this image, which is, anyone can guess the label? Yeah, I hear all kinds of interesting answers like landing strip and so on, but the answer is two spotted ladybug. I have no clue why. I tried to focus on, there are spots here, and there is these numbers. Maybe it's like bug 2000, or maybe the annotator was drunk or something, but those are the kind of things we all the time see in the data. The last one, I won't share the label. Anyone who wants to hear about the label, come to speak to me at the office hours. But that's a real image from ImageNet. I also removed the image name, but anyone who wants to get the idea of the image can come chat with me. So overall, we've seen this is a pretty annoying problem, and it may slow us down. And both in Apple and also Amir, my collaborator, encountered it in his own company doing automotive, deep learning for automotive. So we spend a lot of time building the model. We found out the data is super crappy. The model is failing. We have to recollect data, re-annotate data, and so on and so on. We spend a lot of cloud costs. We spend our own time, which is the most important thing, probably the most expensive thing. And again, our ability to get models into production is very, very slow because of all those data issues. And then it got us thinking, can we do something better to help understand, clarify what's going on with those visual data sets? So what we started to do is the thing we are good at. We started an open source project, yet another open source project called FastDo. We started it a year ago. It's been super, super popular. We crossed the 250,000 installations. And that only shows that this is very useful. What we do, we provide basic building blocks when you have visual data and you want to curate and clean it, things like finding duplicates, corruptions, outliers, wrong labels, and so on. Now, when you ask a computer vision researcher, do you know how to find duplicates? They say, oh, that's a very easy task. I know how to do it. I don't need any tool. Why should I need a tool? I can write, I do this feature vector embedding, and I do this clustering, and I do whatever, vector DB or whatever, and a few steps, and I can solve it. But the problem in practice, companies don't really know how to do it properly, especially companies that don't have very strong deep learning talent. And they may want to, they may even not have programmers at all. So we started with FastDupe. It started to be very popular. After we crossed the 100,000 user mark, we got outreach from multiple VCs. So they said, go take money. I found out they have some tools to track these kind of things, the progress on GitHub and so on. So that's a good 100,000 users, a good watermark to get funding. And we got funded by Insight and Madrona. Now, what's unique about, and we do have tons of users, and most of them, of course, we don't know because it's a Python package. But what's unique about FastDupe is that we designed it to be deliberately simple, which means the input is a folder of images, the output are some insights from this folder images. There is no complex interaction in order to feed the data in. It's super efficient. It's written in C++, so under the hood there is code which is not fully open source, which is it's more of a freemium package. And we don't use GPU at all, so that was a design. And we can scale to 1 billion images on a single multi-core machine without GPU at all. So that's one of the benefits of doing things very efficiently in C++. In addition, it works for a wide variety of datasets. We see and that's what I used in the title, and I show you a little bit of those datasets. And it runs on Linux, Windows, Mac. It runs on the local vicinity of the customer, so it's pretty easy to get started. And of course, it's a free tool. In terms of performance, for this full ImageNet, the full analysis I showed you in the last few minutes, FastDupe can do it on a pretty weak multi-core machine, 16-core, with a cost of $1.25 on a spot instance or $5 on EC2 instance. So the compute is very, very efficient. Now, in terms of what's behind FastDupe, we connect to the repositories of or buckets of visual data, images, also video. We construct a graph of all the images together in order to understand what's similar or what's different. To the graph, we also add metadata about captioning, locations, anything, bounding boxes, and anything which is related to the images. And that way, we are able to find those interesting buckets of information, that what are the duplicates, what are the outliers, what are the mislabels, and what's the high quality. Now, this can run as a pipeline for programmers, data engineers, or it can run as a system for analysts that hopefully, if all the video will be working, I'll show you also how it looks like. So that's the system. In terms if anyone is wondering what's behind it, and this is we are kind of one-trick pony. So our previous startup was based on our academic research at Carnegie Mellon. We published a few papers about GraphLab. That's we did very large-scale graph analytics. So we are graph guys, and we know really well how to deal with graphs. Now, in a funny anecdote, we just got a VLDB Test of Time Award for this paper, so it's 11 years late. So when I interviewed for academic position, they said, no one understands what you're doing, and you have like 3 citations, and you're not accepted. So I'm a failed academic, but 11 years later, the award came. That's very influential paper. We got tons of citations. And what's behind GraphLab is the ability to do a very efficient multi-core and distributed computation for graphs. Now, of course, I won't get into too much detail. Anyone interested is welcome to look at the papers. But what's the trick that we did here? We say we are computer vision people, but we also understand really deeply graphs. So what we can do feature vector embedding with nearest neighbors clustering, and then all those relations are entered into the graph, and we can do all the operations on the graph itself. So we can do community detection, we can do graph searches, we can do all kinds of analytics on top of the graph. So that's what we do. Maybe a little note about I hear here in this conference, most of the activity and excitement are around vector database. So as someone who likes to think a bit differently, I can tell you my stance about why vector-based are only a part of the solution, not the full solution. So imagine you have images, and each image is, you go to the vector database, you find 10 most similar images, and then you're happy. The problem in real practice, there is very skewed distribution, and the image may be very similar to 1,000 images. So what you need to do is query the vector database, find those images, and then query again, find more images, and then query again, find more images, and start to get into recursion. Now, a vector database cannot be efficient as a graph structure when you want to understand the full syntax, like structure of the world of the images. And that's why it's very limited in the sense you have to re-query it each and every time in order to understand the graph structure, especially if you want to find, for example, a path. So then you get into very big recursions. So that's our philosophy. That's how we do it. I promised in the title, I promised a little story about mosquitoes. So I'll tell you. So this is our first paying customer. It's me and Amir here. We got super excited. We met their CEO. I won't mention the name of the company from obvious reasons. But they had 4 computer vision scientists working on classifying mosquitoes. It's a real use case. The mosquitoes cannot reproduce, and they are being released in California. I don't know where, but should probably help you in some indirect way in order to reduce mosquito population. So we got the task that the model is not performing, the CEO is anxious, and they really want to improve the model quality. Now, they had 4 computer vision people. One is an expert in Siamese network, one is an expert in feature vector using XGBoost, and each one is a different expert, and they have entomologists, that's a word that I didn't know. I'm also not, I don't know if you know it as well, but they're very highly paid mosquito experts that mark each and every mosquito to see which type of the mosquito, and the goal is to classify the mosquito population in nature. Now, what we started to do, we looked at their data, and we found the quality of data was pretty poor. So while they're always working on the algorithms and the high level and things that are more advanced, they didn't clean the low level, like corrupted images, outlier images that are not mosquitoes, badly cropped images, and so on. Issues with labels. Imagine you have a crop of 100 mosquitoes, the image was not cropped well, there is a single mosquito, and so on. And when we started working with them, they had this potential objection to say, you're not mosquito experts, and we have this special kind of mosquitoes, and this one has the yellow tail, and the other one doesn't have a yellow tail, and it's very minorly visible in the image, and that's completely different, and if you mistake there, we're totally screwed up. But once we clean the data and show them what's going on there, and they remove all the issues, suddenly the model significantly improved, and they were pretty happy, and they were our first paying customer. Now, of course, I'm not showing their data. This is a Kaggle data set, but again, we just try it for the illustration, and each image there was appearing 4 times in different rotations, which is, again, something completely useless, blows up your data size 4 times, and that's very common, at least in any mosquito data set. Now, the last thing I want to show, and I'll be brief because I know lunch is coming up, so I'm also a mindful speaker. So I want to show you a demo how our system looks like. So I said there is some promise working with graph. It should be interesting, but how does it look like when you traverse a real data set? So what I'll show you here is a data set, a Homeland Security related data set, satellite imagery, agency called Mafat. That's a public data set that we found to be interesting. And what we got here, the task is to find objects of interest that could be boats, airplanes, and so on, containers, buses, medium trucks, and all kinds of things in satellite images. So this is what the system we built. It's also free to try out, and that's our cloud version of the open source. So if you don't want to pay anything, use the open source. You want to have more advanced feature, you can use the cloud version. And what we have here, we have a global view of what's going on totally in their data set, so an analyst can explore images. whenever they click into one more level of zoom in, they are traversing this graph we built to see more and more similar objects until they get to the lower layer. And what's else interesting is that analysts now don't have to work one by one. They can just click this domain of 500 airplanes, do a single annotation, and then they're done with the task that otherwise they have to do manually one by one. We can also find bad data points, mislabels. In these examples, there are small airplanes. So we find issues where there are completely nothing there, and it was marked as a small airplane. This is a very high quality data set. It's part of the competition. So the companies that are competing on this data set are scored by this data set. So if there is a mistake in the ground truth, it means companies losing score, although we can very quickly identify a lot of issues with their data and then allow to fix them. Yeah, so overall, this is what I wanted to present. Anyone working on images should try our free GitHub project. This is our cloud project. This is my email if anyone is interested in communicating. And we have time for a couple of questions, if any. Thank you. Yeah.
So in a situation where almost all the images are completely different from one another, how does your approach help scale the data labeling process?
Yeah, that's a good question. I will repeat it if anyone didn't hear it. So the question is, when the images are not completely identical, how our process can help scale the annotation process. So we build a graph of connections if we do n-dimensional embedding into a specific point. So if all the images are completely identical, they are boiled down to the same point, and you have a region which is not interesting and has many, many copies. Now, if the images are very, very similar, they are very nearby on this. They have edges that are very short to this point, and so on. And we did test it to a wide variety of data set that, let's say if we have score 0.99, a human can know this. I'll show you two images, you won't know what's the difference. There is some minor pixel values or maybe a 1 pixel shift in the object or something like that, but it's not visible. And as you go lower, there is a crude approximation. So if you have elephants from different viewpoints and so on, they probably will have a score of 0.8. So you as a user, you can fine-tune those thresholds and use the one which is more appropriate for your task. Yeah.
I'm just wondering, on a technical level, do you guys have to build specific hash function for each data set? That's the term we described nearby, right?
Yeah.
Universal functioning, or it's a specific for each data set?
Yeah, so the question was, do we need to build a specific embedding function for each type of data set, or we use general? So what we did something super general. We did something that works in 95% of the use cases we've seen, which is a very light model. It takes 2 milliseconds to score on a single core. So a 16-core machine can score around 8 million images an hour, and we don't use GPU at all. Now, if the customer has very specific knowledge, for example, in a mosquito case, there are mosquitoes with this yellow tail, and they have an embedder which significantly different vectors with yellow tail, without yellow tail, we can feed in the customer embedding, and then it's totally fine. And it's also supported in the open source. Yeah.
Can you comment on the technology between convolutional and Gaussian? Are those core technologies to your system for image identification? Convolutional neural network versus Gaussian, those technologies?
Yeah, so the question was, can I comment about technology of convolutional versus Gaussian? So if I understand the question, you're relating to low-level feature building in order to identify edges and things in the images. Our embedding is based on deep learning, which means there is a complex network structure which cannot be fully explained as a convolutional or Gaussian, but it's a combination of a few layers and a few building blocks and so on. So that's it's not one-to-one. It does provide very good visual results. So that's the quality. So if I showed you the demo of the airplanes, and you see all the airplanes are clustered together and all the boats clustered together, then for us it's a good measurement. If a human sees the similar objects are batched together properly, that's a good approximation to the quality of the embedding.
So on the quality aspect, is resolution more important than algorithm? Do you look at it that way?
Yeah, so there are multiple aspects. We've seen datasets that need special embedding. There is a problem with resolution, for example, in satellite imagery, where the images are very, very tiny. There could be 5 by 5 object in a 5,000 by 5,000. That's a drawback because we assume a fixed input image. So you basically lose some information if you go on very small images. We've seen a lot of different data sets. We've seen heat maps. We've seen radar data sets, a lot of different things. So there you may need a bit of different embedding. But for natural images, we have embedding that are working really well. Okay. If there isn't any last question, so I'll let you go to lunch. Okay, my office hour is 2 p.m., so I would love to talk to anyone interested.